Okay, this is a short lesson. It's simply a review of my vector analysis, and there was some questioning on it. Some people didn't understand it, so they questioned it. Well, today I went to see a physics professor just to double check, and he's a chairman of the physics department. And I explained my vector analysis with him. I'll show that again up here. This whole thing, this whole vector analysis, I explained the entire thing. Starting here, all the way down. And he agreed with everything. He said everything was spot on, correct, except he disagreed with one point, and I want to bring that up today, discuss that. And I got him to see what I was saying. Okay, so I'll explain that down here. Let's see. Okay. All right, so I saw this professor and he agreed with my entire analysis except for my analysis of inertia. I'll show you the diagram again. He said my vector analysis was totally correct, although extremely complicated, he said, if not impossible to quantify mathematically. I agree, given the fact that the center of mass is only an approximation. All right, we're taking that center of mass as where the inertia gravity force originates, and that the body is actually radically changing positions constantly while skiing, and that the upper and lower bodies move separately, although not independently. Right, they're connected, but they move separately. All right, it complicates things. Should you take the center mass of the lower body plus the center mass of the upper body independently, and so forth. All right, anyways, but I finally got him to agree with me on my analysis of inertia. All right, so I'll show you what he disagreed with. So this is my diagram that I showed you, that in angular motion here, all right, the force vector is directed towards the exact center of the circle of the arc. And because that's the direction of force, that's the direction of acceleration, because acceleration is caused by this force. So they have to be in the same direction. I said inertia is directed exactly opposite. This is momentum at that instantaneous point of the object. It's going to arc around, keep going like this. But at that moment, if you let go, it's going to fly out this way. All right. Now, he disagreed with this. He said, well, one, you can't make a vector with inertia because it has no units, all right? It has no magnitude, has no direction. And I said, oh, well, that's not totally true, all right? Sure, it doesn't have units. Sure, it doesn't have magnitude in and of itself. I mean, momentum has magnitude, which is related to inertia. But that inertia has a direction. He said inertia is going in this direction. I said, no. Inertia is a resistance to change in motion. All right. And I eventually convinced them. And here's how. Let's see here. What's going on? All right. So I showed him my diagram below, and he agreed with everything except inertia. He disagreed with me he disagreed with me from a purist standpoint. I say purist standpoint. He said inertia is a concept and it is unitless and therefore has no direction. I said, okay, but I explained this. Inertia is a resistance to a change in motion. That's Newton's first law. Newton's first law states every object will remain at rest or in uniform motion in a straight line unless compelled to change its state by the action of an external force. Okay? Now, acceleration is a change in motion. Okay? That's what acceleration is. It's a change in motion, right? Therefore, inertia is a resistance. Because inertia is a resistance to change in motion, inertia, therefore, is a resistance to change in acceleration. All right? Now, except for gravity, all acceleration is caused by a force. Remember we said gravity is a special case because gravity is not caused by a force. Gravity is an acceleration, not a force. And it is not caused by a force. It's caused by the curvature of space-time. Right? And this is Newton's second law. Force equals mass times acceleration. So when you have a force, that causes an acceleration. A net force, I should say. Now, Now, acceleration is in the same direction as the force that created it. Now, that's obvious. The force creates an acceleration. So if you apply force this way, it's going to accelerate in that direction. All right? Now, this is where inertia has direction. Inertia is a resistance to a change in motion. If you apply a force to something, it's going to cause it to accelerate this way. Now, it doesn't want to accelerate, so you have to apply a force. It's going to resist. The resistance is in the exact opposite direction. So if I have my laptop in front of me, and if I push it with my palm, it's going to resist in the opposite direction. And that's Newton's third law. Every action in nature, there is an equal and opposite reaction. Opposite. Okay? So if this is a force and this is an acceleration, let's say this is a force or acceleration, whatever, this is the resistance, right? The resistance, the object is not going to say, oh, all right, I'm going to resist you this way or this way. Or I'll go with you. I'll help you. No, it's going to resist in the exact opposite direction. That's the point of resistance, right? So inertia has a direction. Now, it is exactly opposite. If these are pointed towards the center, this is pointed exactly outward, right? And that's why if you, like I showed you this example, if you swing any object in front of you, if you spin in a circle, that object will go out straight in front of you. Now, as you start to accelerate from nothing, it's going to lag behind a little bit, but once you get it up to speed, it'll be right in front of you, right? That's due to that inertia, okay, which is the resistance to a change in motion. So this is why the kid is straight out and not off to the side after accelerating to constant speed. All right. So I eventually got him to agree with me, although I admit inertia cannot be considered a vector because it has no units or magnitude. But you can clearly say it has a direction, which is directly opposite to the direction of the acceleration, which it's trying to resist. Right? Now okay, I'm gonna stop there. So what that means is when I showed you the vector diagram, right? For example, let me show you this one, right? Now, if you lift your upper body center of mass, that inertia gravity vector is going to be pointed directly to the outside of the arc, right? Directly opposed to the acceleration, directly opposed to this force, which is the centripetal force pushing you in, or I called it the ground force to keep it simple. All right, that's it for that lesson. Hopefully that made sense.